Hi everyone. Today we'll take a look at the next part of permutation combinations, which actually involves combinations itself, or also known as selections. So if you briefly recall, in the first initial minutes of the previous video, I had discussed what separates permutations and combinations, and I had mentioned that the standard thing that we usually hear from our professors or our teachers is that in permutations order matters and in combination order does not matter, right? So let me give you examples. Okay, let me so it's easier to understand of what's actually happening. So in combinations, we're not really caring about if we make a certain selection. We don't care about which came first or which came second, as long as they were selected. So, for example, the most common example, like the most common thing I can think of, is a team selection. Let's say you're making a basketball team, and you need to create and you have to pick the starting five, right? And you have a team of squad of 15 players. So it doesn't really matter who's your first pick or second pick, as long as the certain five people are picked at the end of the day, right? So the order of picking doesn't matter. If the order mattered, like who's your first pick that matters, who's your second pick that matters, then you would have permutations because you're actually arranging them in terms of preference. But if you don't have a preference, then it's just a combination because you just care about who's being selected. Similarly, I'd also mentioned the handshake, given the handshake example in the last video. So same for the handshake video, right? So let's say there are 10 people, right? Handshake. If person A handshakes with B, then B by default is also shaking hands with A, right? It's just one. It's like, let's say let's say Liam Hemsworth, and Chris Hemsworth, right? They're brothers. Chris Hemsworth. They're brothers, right? Liam can say, "Oh, Chris is my brother," or "I'm Chris's brother." They're the same thing. They mean the same thing, right? It doesn't matter, right? So in such situations where it doesn't, things don't matter in how they're selected, that's when you go for combinations. Again, I'm just reiterating this so that when you do face questions, you're not confused of whether it's a permutation question or whether it's a combination question. All right. Okay. So let's just take a brief look at what I've written here. So it says number of ways of selecting R objects out of n available distinct objects. Again, distinct being the keyword here. Okay, let's address this concept with a really quick example. So we have how many ways two boys can be arranged out of a group of three boys. Okay, so arranged is permutation. Okay, because their arrangement matters, whether A comes first, whether B comes first, whether C comes first. Selected, they just need to be there. Doesn't matter how they're there, they just need to be there. Let's say we have three boys, right? Boy 1, boy 2, and boy 3. Right? Now, out of these three boys, we need to arrange two boys. So first arrangement can be just boy 1 and boy 2. Second arrangement can be boy 1, boy 3. Third arrangement can be, let's say, boy 2, or you know what, I'll do it here. Third arrangement can be boy 2, boy 1. Fourth arrangement can be boy 3, boy 1. Fifth arrangement is 1 is here, 1 is here. Let's say boy 2 and boy 3. And the sixth arrangement is boy 3 and boy 2. Now, if you look closely, arrangement is where the order matters. That's why I have 6. So if you think about it, it's like the same thing as, let me change the color. It's the same thing as 3p2, which is 3 factorial by 1 factorial, which is 6. And hence we have 6 arrangements. But, well, for selections, this is 1, boy 1 and boy 2. This is another one, and this one. The rest of them are just, kind of the complementary version of each other. So how many selections can we have? Well, it's boy 1, boy 2, boy 2, boy 3, and boy 1, boy 3. And here, what we've essentially done is we've taken the permutation, okay? We've taken the permutation 3p2 and divided it by the number of arrangements that we have, our arrangements, by like 2 factorial. And this essentially gives us 3, which is another way of writing 3c2. Now, for those of you who have actually, looked at or studied combinations before, now you can understand how this, how selection varies from arrangement. So, if I have to, explicitly state the relation, our NCR is NPR by R factorial. That is why NCR is equal to N factorial by R factorial times N minus R whole factorial. That's why. Okay? And then if you want, you can kind of elaborate this relation as well. NPR is equal to R factorial times NCR if you want. I mean, there's nothing much really to it, but I hope you get the idea from where it's coming from, right? That's literally it. The way to get combinations is by reducing or removing the repetitions by dividing by R factorial. That's it, literally it. There's nothing more to it. Okay, let's start with a very basic example. I'm sure you've already come across these questions. If you have not an issue. Let's solve it. Okay, so we're told that we have to create a team of 4 boys and 4 girls. That's our requirement. Okay, out of 6 boys and 5 girls. So how do we do it? Okay, so what we do is we break it apart. First, we do the individual selection of boys and girls. So first, okay, I've completely misspelled that. Let me fix it. Let's make the individual selection of boys. Okay, so we have 6 boys and we need to select 4 out of them. So N is equal to 6, R is equal to 4, and it doesn't matter in which order they're selected, so hence it's a combination. Okay, their arrangement doesn't matter. Doesn't matter if boy 1 is selected before boy 2, or it's not important for boy 2 to be selected before boy 1. Doesn't matter. As long as a certain boy 1 and boy 2 are selected, that's what matters. Okay, so our selections, the number of selections we have is 6C4. Okay, 6C4. Okay, so 6C4 is for boys. Now for girls, what do we have? Well, we're gonna have N is equal to 5, R is equal to 4, so our selections would be 5C4. So now that we have the number of selections for boys and girls, what do we do now? So we actually multiply each of them. So, and I'll tell you why. We have 6C4 times 5C4. And the reason for that is there are essentially, let's say 6C4 is some number, let's say 20 for example. I'm just creating some random number. I don't think it's 20, but let's assume it's 20 for now. If it's 20, and that means there are 20 different selection of boys. This can be, boy 1, boy 2, boy 3, boy 4, or it can be boy 1, boy 2, boy 3, and boy 5, right? There can be like 20 such odd different selections. Same for girls. Okay, so each of these boy selections can match with each of the girl selections. Let's say there are, 20 boy selections and 10 girls. So each of the 20 boy selections can match with each of the 10 girl selections. That is why, so each 10 girl, so there are 10 of them, so 20 times 10. And that is why we multiply each boy selection with girl selection. So I hope you remember. I hope you know this property. If you don't, I'll just share it really quickly, and I'll change the color as well. NCR is equal to NC N minus R. Okay, this is derived from the Pascal's triangle. If you have studied it, it's great. Otherwise, you can just hardcore memorize it. That's not an issue. So essentially, if this is in the non-calculator section and I have to solve it really quickly, I can just do 6C2. It's the same thing. So essentially, this can be either this 2 and 4 this must be adding up to 6 every time. So either it's going to be 6 minus 4 is 2, or 6 minus 2 is 4. So 6c4 is equal to 6c2, and I can call this 5c1 as well. 5, because 4 plus 1 is equal to 5. Okay, so 6 factorial times 2 factorial times 4 factorial times 5 factorial by 1 times 4 factorial. Okay, so 5 factorial by 4 factorial, that's basically 5. This is 6 times 5, which is 30. 30 divided by 2 is 15. So I have a total of 75 selections. In 75 ways, a team can be made. Okay, next question. In how many ways can a team of 4 boys and 4 girls be selected out of 6 boys and 5 girls? Same situation as the previous one. If a particular boy and a particular girl refuse to work together. Okay, this is interesting. Let's break it down. Okay, let's say we have boy 1, boy 2, boy 3, boy 4, boy 5, and boy 6. And we have girl 1, girl 2, girl 3, girl 4, girl 5. Let's say for instance that boy 6 and girl 5 are brothers and sisters, and they don't want to work together because they're brothers and sisters. You know, it happens sometimes. Okay, so let's say that, okay, I'll just change the color, take yellow. Let's say that boy 6 and girl 5 don't want to work together because they are siblings. Okay, so now there's one method. Okay, one option is boy 6 and girl 5 are both not selected. Not selected. Okay, there's another option. Boy 6 is selected, but girl 5 is not. Okay, our third option is the inverse, or the converse, you could say. Boy 6 is not selected, but girl 5 is selected. Super simple, nothing too crazy. Okay, so I've just broken it apart. I've taken all the possible combinations, right? Obviously I can't take the one with when they're both selected, because that's the one they're not supposed to be. Okay, so if I take the first situation, so this is what permutation combination, this entire chapter is about. It's just breaking up things based on the given information, right? You probably spend more time actually thinking of the situation and, you know, setting up the question, setting up your answer, than actually spending time on calculation. Okay, so if both are not selected, then that just reduces our workload. Now we only have to select from 5 boys and 4 girls. That's easy. So then our selection is based on 5c4 times 4c4. Super simple. For the second situation, we have 6c4 times 4c4. Third situation, we have 5c4 times 5c4. Now, if this is what you have done, think about it just for a second. There's a slight error in this, okay? The error is the second and third case. In this situation, second situation, we've already claimed that boy 6 is selected. If boy 6 is selected, this can't be 4. It must be 3. Okay, and this has to be 5. So this is actually supposed to become 5c3 times 4c4. Similarly, if we've already claimed that girl 5 is selected, then this must be 4 and this must be 3. So this setup should be 5c4 times 4c3. I hope that makes sense. I wanted to show what we can initially do wrong, and then I wanted to show, you know, what we have missed, the missed perspective. Okay, so now if we go, okay, there's no space here, so I'll try to condense it here really quickly. So 5c4 times 4c4, well, that's 5. 5c3 times 4c4, That's 10 and 5C. 4 into 4C3, well, that's 20. So now we don't multiply this. These are different independent cases, okay? They're not related to each other. So we don't multiply these. We just multiply the initial selection between each case. So we just add them up. So 5 plus 10 plus 20. So that's 30, 35. So we have 35 ways, okay? Again, there was a subtle trick to it, subtle catch to it. But yeah, that's about it. Otherwise, I don't think solving this question was that difficult at all. Okay, let's go to the next one. Again, same team selection type question. Let's give it a try. In this question, we have a debate club consists of 6 girls and 4 boys, a team of 4. So to be selected from this club, including the selection of a captain from for the team. The team has to include at least at most 1 boy, and the number of ways of selecting the team is 1. Okay, very simple. We have 6 boys. Oh, sorry, I apologize. 6 girls. 6 boys was in the last question. 6 girls and 4 boys. Okay, so in our first condition, let's say we have no boys, right? So we have 6 girls from 4 being chosen for 4, and now we also have to select the captain. So the captain would actually be selected from the 4 people that are the 4 girls that are being selected, and 1 captain. And that's it. Okay, so 6C4 times 4C1. Our second option, this I'll just call it, no boy. Okay, no boy. Okay, now we have 1 boy and 3 girls. So in that situation, we'll have 4C1 times 6C3, and from these 4 people that are selected, we need 1 captain. Okay, so we have 4C1 for this captain. Okay, this captain and captain. Okay, so this is 1 boy and 3 girls. Okay, so let's simplify this down. What do we get? Well, we get 6C4, so this is 6 times 5, which is 30. 30 times 4 is 120, but I think we have to divide by 2 as well. I think I've missed somewhere. Wait, so we have 6 times 5 times 2 and times 4, and then we have 4 times 6 times 5 times 4 by 4 as well. So I think, yeah, so this is 60, and this will be 320. So total we have 380 selections. Okay, the catch in this question is obviously the captain part, because we have to select a captain as well from these arrangements or the selections. That's why we choose 1 captain as well. Final question for today, and we're asked that a box contains 2 white balls, 3 black balls, and 4 red balls. In how many ways can 3 balls be drawn from the box if at least 1 black ball is to be included in the draw? Okay, okay, so again, why is this a combination, not a permutation? Well, if there are 2 white balls, let's say W1 and W2, and I pick the W1 first and W2 second, it doesn't matter. You can't really differentiate between them, right? So that is why we're not using permutations. We're just trying to figure out how many selections can be done, because they mean the same thing. Okay, so let's break it apart. Okay, so let's write it down. We have 2 white, 3 black, and 4 red. Okay, so Let's break it down again. Okay, so for one, if we have one black, right? So we need at least one black. So if we have one black that's taken, okay, we'll have 3c1 times 6c2. And the reason for that is we have 3 black. So this is the one that's already selected first. Okay. Now 4 plus 2 is 6, and we don't really care how many of them, which red ball, whether it's a red ball or whether it's a white ball that's selected, because the question hasn't restricted us in any sort of way. Okay. So we take one black, so we have 3c1, 6c2. Similarly, if we have 2 black, we have 3c2 and 6c1. And if we have 3 black, well, that's pretty obvious, that's just one way, but I'll still write it down. 3c3 times 6c0. Okay, nothing else. Now we just got to add each of these cases up. Then they come out to be a grand total of 64 selections. Okay, so now this was actually one method you could do it. Okay, there's another method for such questions, and that is, kind of taking the extreme case. So what we do is we take the total and we subtract it by no black ball selected. Okay, so in this situation, if the total possible cases are, without any restrictions, are 9c3. Now if no black ball is selected, it's just 6c3. Basically it's like 3c0 and 6c3, like this, right? So now if you simplify this, what do we have? We have 9 times 7 times 8, sorry, what am I doing? 9 times 8 times 7, we have 9 times 8 times 7 times 6 factorial, which is the same thing as 6 factorial and 3 factorial, 6 times 5 times 4 by 3 factorial by 3 factorial, okay? 84, and this is 20. So total of 64 ways. Again, same answer, just a different approach. Whatever you like, you can always take. This is a very common question in the IB. Easy 3 to 4 or even 5 marks for this question. I think this is a very standard approach. You can pick whatever you like and go about it. So this kind of sums up selections or combinations. There are some properties which I might discuss later in another video, but moving forward, we'll take a look at more special cases such as circular arrangements and maybe other sorts as well. So this was all for combinations, and I'll see you in the next one.